We present an algorithm for frame interpolation for dynamic scenes that leverages implicit flow encoding and interpolation. Given a pair of images I0 and I1 of a dynamic scene, frame interpolation aims to synthesize an intermediate frame IT where T defines the desired temporal position. Frame interpolation can be used for many applications. For our work, we target the use case of generating captivating videos from near duplicate images. While state-of-the-art approaches produce interpolated results with high quality, they are limited to cases where the two source images have consistent brightness and illumination. In practice, however, the two images could have different brightness and illumination, even if taken shortly apart. Most state-of-the-art approaches are flow-based. They first estimate bidirectional flows, then use these flows to warp the input images. The final step is to blend the warped images to produce an interpolated result. Our key observation is that their estimated flows degrade quickly in the presence of illumination changes. We propose to utilize existing pre-trained optical flow methods that are robust to lighting changes. However, we can only use them to estimate the flows between the source images. For our use case, we require interpolated flows. We estimate the intermediate flows using a coordinate-based neural network that takes xy spatial and t temporal coordinate as input and outputs a 2D flow. We optimize the network to encode the two reference flows. Once converged, we can query the system at intermediate t to obtain the interpolated flows. A single coordinate-based network cannot properly encode the reference flows. In this synthetic example, we can visualize that it generates the in-between results by averaging the data at the observed coordinates. Encoding each reference flow into a separate network produces independently encoded flows that are not interpolatable. To address this problem, our solution estimates the weights of the coordinate-based network using a hypernetwork, thus encoding the two flows simultaneously in a constrained high-dimensional space. At inference, our solution generates interpolated flows from t input coordinates. We combine the warped images generated by these flows using films blending to create the final result. We compare with two state-of-the-art methods, ABME by Park et al. And film by Reda et al. This scene contains no rigid motion in an indoor setup. It illustrates how natural light can change significantly even for photos taken seconds apart. Note the blurry estimations by ABME and the disordered head by film. Our results are shown on the right. Our method significantly outperforms previous methods in this outdoor scene featuring rigid motion. In this example, ABME produces a blurry background and film is not able to properly reconstruct the gaps in the chair. Our approach produces a high quality result without any objectionable artifacts. We provide additional results that show our method's ability to handle lighting changes.